There we go.
That was awesome.
That was so sick. Shout out to Brad for that remix. It sounded way better than it did in my head when I pitched it, to be honest. All right.
All right.
Can you see if people are in the chat? Or should we wait a minute?
I say let's just go for it.
Let's just go for it. All right, folks. I guess we should introduce ourselves first. Max, you want to?
Sure. I'm Max Harley. I'm a principal security researcher at Dreadnode, and one part of the World's blog.
That's right.
We're here. Shane, who are you?
I'm Shane. I am the ML half of the World side of things. I would say that Max is the person who keeps me honest from a security perspective and make sure that I'm not making things up. And I make the gradients go in the right direction. And that's sort of the split. So today we're doing what is essentially like a DVD commentary of our blog. You know, like
Director's cut.
Yeah, director's cut of World's simulation engine for agentic pentesting. The goal here is sort of to start essentially expanding on what's in the blog, sort of our motivations, how we designed it, our initial set of results, and then like what we think is coming next. I guess we'll start with the sort of top line result. So we trained a fine-tuned an 8 billion parameter model that went from essentially scoring 0 on Go to it was not able to pop any users, any hosts, any domains, to a model that could get domain admin on the north domain and Go, game of Active Directory, which is a fairly common lab that's being used in these sort of agentic pen testing evaluations. And we did that with no actual data, no distilling from frontier models, no online RL. This is data that we created from whole cloth. And we were able to, using Worlds, the technology we'll talk about today, get that result out of a pretty small model. So we'll just take it from the top, I think, starting at the sort of top heading of the blog and work our way down. We'll start with small models in security. Small models, like small here means something very different than it used to. We'll say anything below sort of 70 billion and down compared to sort of what we're being served from frontier models. We've seen some getting a slight amount of echo, I think.
No, for me.
I think so.
I'll just mute, see if that's better.
Sure. We've seen, particularly in software, benchmarks like SweBench or SweBench Verified. We see a new frontier model drop from OpenAI, Google, Anthropic, and sort of within the next 12 months that follow, generally that performance is matched by some open model or multiple open models. And what that is sort of meant or implies is that for any given like time period you're in, if you are satisfied with the performance of a model and you wish you could do it, you know, with private inference that you owned, you're sort of in a position where you're waiting for 12 months, and then it's quite likely that you can do that, at least for software, maybe less so for security. Max, you actually did a project that was extremely popular, the Living Off the Land, and you used small models. What were your experiences with small models in security?
It wasn't good. I mean, it was all right. The models performed fairly well. This was the first blog post I did in that series. The inspiration was Lock Prompt, which was a NYU project. They used one of the big labs models, and they integrated a Lua engine into one of to write Lua code that performed post-exploitation activity. It was actually just ransomware. It would generate a ransomware sample and then run it. And the cool thing about it was that it was different every time. I sort of took that idea and well, what if it wasn't just ransomware? What if you actually performed a red team or something simulating that? It was using a Lua engine called Sol 2 and a local model. So it used the 5.3 model that comes by default now. So this model is integrated on Windows Copilot Plus PCs. So in theory, you could drop a binary to disk with this integrated Lua engine and run it all locally with all local inference. And it was able to do local privilege escalation sometimes after quite a few runs, but it could get there, but it was not very stable. These models are not built for doing offensive security tasks, and that definitely showed.
And the way that you sort of got it to work, and this is my understanding, correct me if I'm wrong, but essentially like these models are trained at least on some level for like software engineering. So you're sort of trying to hide the offensive security within the capability that is strong, which is software
Yeah,
engineering.
exactly. Yeah, and I think that's kind of the most powerful part of that is like if you can like most models now are there's some sort of coding ability that they RL on or they're just putting a lot of code in there. Um, So you already have that latent capability in the model. So instead of doing something, you'll see a lot, doing, a lot of people try to make uh, agents with like tool calls, and not every model is good at tool calling. I mean, more than anyone, like they're not. And so, just using the model for and abusing sort of the coding capability it has is way more effective as like an interface for the computer than trying to do like tool calling and you know have some sort of tool associated with that to perform the operation on the host.
Yeah. Yeah, I agree. And I think that the one of the things that has been interesting about our work over the last like year or so is how much we've benefited from models improving when we can formulate our problem in a way that is like software adjacent. Essentially, if you can take advantage of what the labs are focusing on improving the models on, then things tend to go well. But I will say that that underlying model of how offensive security is intended to work often seems to be sort of what is lacking, like the understanding of like they understand how to interface with computers through software and for the better models through tool use, but sort of the exact understanding of what is a like strong offensive security flow is often like not top of mind when you start like sampling from those models. We tend to find things that are closer to what I would say like script kiddie write-ups maybe is the offensive way to put that, but like nmap into Metasploit into call it a day. And we'll I guess the that brings us into the training data problem of it all. So if you think about like, okay, small models are very, very good at software, punching well above their weight for what we'd expect. Um, Security is sort of lagging behind. Well, why is that? There's a lot of software data, as it turns out, for any part of the stack that you're interested in. So if you're interested in pre-training, there's a lot of places to get just code. If you're interested in sort of task instruction fine tuning, it's very easy to get data sets of PRs that you could think of as a prompt or an issue, and then like a completion, which is the software. And then from a post training perspective, uh, very easy to set up a Docker environment. Oh, well, very maybe very easy is too strong. When I say very easy, you should read that as tractable, right? So easy to set up Docker containers that are running these software, like accepting patches, checking unit tests against them to do like RL for or what have you. And then you try to imagine how to move that over into the security space. And I think it's a lot slower. And a lot of that has to do with availability of data and also like infrastructure. So like I guess one question I'd ask you, because you're better sort of prepared to answer it, what you have been a pen tester professionally, how many write-ups do you think reach like or what percentage of write-ups do you think are like intermediate or above tier about like offensive security? Like if you were just crawling through the internet.
Going through the internet, well, I think the problem is, it's going to be hack the box write-ups and people illegally doing like OSCP write-ups for the labs that they did.
Yeah.
There's just not much of that data. I mean, obviously, pen test firm or the SpectropS's, Trusted Secs, the MDSec, like those guys are going to have real pen test write-ups. Everything that you're going to find online through scraping is going to be someone doing something for hack the box or
Yeah.
Goad, like these public environments.
Yeah. 100% agree. And I guess the second question then is how reflective are those lab environments of what you saw in your like actual day-to-day career? Like how close are we talking?
I mean, structurally somewhat similar because
Sure.
they're games. Like at the end of the day, Hack the Box is a game, and it's going to be a single host, or if you have something like Rasta Labs, a small network, which is not representative of if you're going to go into a large company as a pen tester and attempt to uh, do a network test. It's like just the scale is so much different in something like hack the box write-ups versus reality.
Yeah, so you mentioned like Goad, as we know, as a network, that's a five-host topology. Most hack the box is one. Without revealing anything NDA violating, like average host that you pen test or average network that you did a job for, like how many hosts we talking ballpark?
Oh, it really depends. Like 1,000 to 20,000, something like that. I mean,
Right.
it's significant. It's orders of magnitude bigger uh,
Yeah.
than those public environments.
Maybe running into some context length issues to go from 0 to
Yeah,
100 for
yeah. You
sure.
do an LDAP search and your context window is broken.
Yeah, I think that's the thing that maybe changes most obviously. Like what the advantage that software has is that the stuff that is publicly available is not. It is different from the stuff that's privately available and the stuff you might want to do at what we would call like our inference distribution compared to training. Um, but it's a tractable change, right? Whereas I don't think that's necessarily true in security. Security to me has always felt like the public training that exists gets you to step one. And then sort of when you're at that step one, then you're absorbed into one of many pen testing firms, and then you're put through trials and tribulations that you can't really get outside of that on the job training.
For sure.
And so that's sort of been, as people who are working on this particular problem of like recognizing that there's not a lot of public data for offensive security tasks, and then trying to figure out how to, as anyone, but as a startup, to like engineer that volume of data. We've considered pretty much everything we list in the blog now as a problem. We thought about it and ran into mostly scaling issues. So like handcrafted labs, that's something like Goad we worked on a lot. We've worked on some other multi-node labs, and they've sort of emerged, at least to me, as something that's kind of better for an eval. Like every time we consider using one for training data, I'm both like, well, that blows an eval that's like public and shareable, which is really painful. And also like you mentioned, the labs that are available are like mostly games. So the idea of like learning priors that are built into that is somewhat stressful to me. They're just, and I don't, because they're intended, like CTFs are also intended to be entertainment, not just like training.
Hmm.
So it's one of my favorite things about the security community is there's like we get a little cute with it, there are little jokes, little puns or whatever. And the language models love interacting with those, but certainly from a like setting up your priors perspective, it is I'm sure you don't run into too many themed node names on the job.
Yeah, I mean, like this is something that I think everyone doing AI and security has come to. It was such a big conversation. If you remember during OAIC, people were talking. I mean, there was David Sachs had a really great, talking point about Josh Sachs. Had a really good point about evals. We need. He was very, just pushed on this idea that like we need evals that are that everyone can use as sort of a you know how is everyone doing at this particular problem,
Yeah.
but then those evals require something like a real environment to set up,
Yeah.
and who's gonna do that?
Who's going to do it? And who's going to share it? And that's been part of the where the handcrafted labs seem to live well there. Like software has so many evals that are both shared widely and sort of easy to share because they're Docker containers, and we just don't live in that world most of the time. So then there's building infrastructure, which is painful for a variety of reasons, mostly iteration time. So one of the things that's like becomes pretty immediately obvious when you try to use self-hosted infrastructure for training is just how slow it is, particularly for Windows. So, if you think of like Go, for example, like the things that have been successful in RL, they're usually games that can be reset with like a single Python function. You say like, oh, I want to go back to the initial state of this board. It's very easy to do. Networks, that's simply not the case. So your like trajectories per second just goes down somewhat dramatically. And when you think about the like full, like the scale demanded by the algorithms that are becoming more popular, it's very difficult to imagine a network that is both large and representative and also easy to reset, right? Those things just don't go together. And I'm sure we're not the only people who have suffered those particular pain points. And also like building variations on those that are sort of meaningful, time consuming, really. Like it's just, and I think people like, I think the correct solution is to opt out of it, which is what we've done with Worlds, but we'll get into that a little bit more. One last thing to sort of note there is like, well, are there people that have access to this data and don't need to build their own infrastructure? And wanted to touch on that sort of briefly. My understanding is when you're doing like a pen test or whatever, you're getting pretty high quality data about the tools you're running and the results, but you can't keep it, right?
No. No, and we've had conversations with people recently about that. That's typically you have some sort of data retention policy. I know in my previous work, I think it's like a 30-60 day policy, something like that, where
Yeah,
all client data after the assessment needs to be gotten rid of. And there's any sort of data that's internal, like you have to, you don't want to handle that. That's a real data about a real environment.
yeah,
That's a responsibility. That's if that got out, that's not good. And that's sort of the professional, um, deal that's being made is like you're doing something sensitive in our network. We need you to be as the pen tester to be responsible with it too. And that's why you don't hire Joe Schmo from down the road to do your internal red team for you. You want to have
that's
a
right.
trusted partner, but that's not great for us trying to build models that do pen testing, because now you can't have that data,
Right,
which
100%.
is reasonable but also frustrating.
Yeah, yeah. I think there's no industry like InfoSec that has naturally generates so much data and can use and share so little of it.
Yeah, truly.
It's a real monkey's paw situation. And we'll talk a little bit now about like how we decided to cut that Gordian knot, but I think that motivates like why we did it, right? There were a lot of solutions to getting data, and most of them were just, I mean, frankly, just inadequate to the scale. When you think about like millions of tokens, trillions of tokens, and then the speed at which you can generate that token count with, infrastructure that you're hosting, either you can't do it, you can't get the numbers high enough fast enough, or you're in parallel putting up so much like horizontal infrastructure scaling that you've spent millions and millions of dollars just to collect like enough data to see if what you got was useful, right? And that, I would say, the thing that the last few years have taught us maybe most, even more than scaling like data or size of models, is that we're going to see the greatest sort of takeoff speed of capabilities depending on how tight you can get that iteration window, right? And maybe that's what Worlds and creating the simulation engine was most about, was like being able to compress our ability to run experiments quickly. So let's talk about addressing the sim to real gap. We might have to speed up. I might be talking too much. So the sim to real gap. No, we'll keep going. Yeah,
we're ripping it.
We're ripping it. This is gonna go for hours. The sim to real gap is something that comes up a lot in particularly robotics. So robotics is, in my opinion, not unlike sort of like Windows network pen testing, very expensive to get real data. So you don't want, like, it's expensive, it's somewhat dangerous, and it's slow. And so when you do that, you don't want to go out into the world with no priors. Like if you were going to train a self-driving car, you want to be like, we'll figure it out on the road. Like you want some bounded understanding of like how this agent is going to behave. And the idea is you're going to create a simulation to do that. And the sim to real gap is this question of like, okay, when I take this agent out of simulation and I actually put it in a car, are there factors now coming in from the inference distribution data that are subtly different in some way than what it saw during training in my simulation that cause this gap in performance? And the answer is like, that's almost always a thing, because it's very difficult to have a high fidelity simulation. This is actually, I hope this isn't a dox for you, but Max, you've been flying planes recently.
True.
Did you get in a sim before you flew a real plane?
Dude, I've got the sickest sim set up. Yeah. Dude, I'm in Microsoft Flight Simulator too much.
I see. We didn't rehearse that question because I knew that was going to be the answer. That's the beauty of this. So I guess my question for you, not as your own sort of learning algorithm, what were the biggest differences between the sim and like the first time you got behind a real plane?
Yeah, I mean there is a difference. That's such a good correlation there, because it is different. There's this idea of like most of the time Microsoft Flight Simulator is very accurate, and you can learn all of your important procedures. Slow flight, stalling, like those are all fairly similar. Landing, you can learn all that kind of stuff. It's not exactly correct. Like slow flight in Microsoft Flight Simulator on a Cessna is not great. It's fairly accurate, but it's not the best. So there's that part. There's also just the feeling of being in a plane, and you actually get way more information when you're in a plane. You can hear how the engine sounds, figure out what your RPMs are, just from hearing it. And the feeling of landing is, like very important to the landing process. So it's a perfect correlation. It's you get way more information when you're in a real plane, but you can learn some super important stuff inside the simulation.
Yeah, that I mean, that really makes like the Microsoft Flight Simulator the ideal sort of simulation, right? Like the way I think about sims is you have some prior that you would like an agent to have, and the sim is a way to construct, like, essentially to transfer that prior. Like if you think about like finding a mathematical expression of reality and just like shoving it directly into weights, like that's really what a sim should be doing. And it's the delta between that, like that simulation you created in the real world, that's you're describing. So like there's a limitation to that plane sim, which is that Microsoft plane simulator is not like jacked into your brain and able to like make you feel weight and like the nerves. You don't fear for your life in Microsoft Plane Simulator, perhaps. Things of that
No.
nature. And that's what made like when Worlds became a conversation before it was a research project, the idea of a lot of people have attempted to create these simulations for networks. And historically, it had always struck me as almost not worth doing because it was so hard to get the fidelity to where you wanted it to be. Or rather, it was so easy to fool yourself, I guess. I've worked with a lot of people, particularly people who are interested in what we would call like classical RL, where no language model involved, just straight RL, multi-arm bandits and things of that nature. And they would sort of construct a sim in a way that felt to me like they knew their tool was a hammer, and so they tried to make their problem a nail, right? Like if you think about what like when AlphaGo happened, like tensors were a very natural fit to represent Go. Like you could say like, okay, I'm stacking a series of matrices that look suspiciously like a Go board. And I'm going to say the white stones are ones and the black stones are negative ones. And bam, like I've got the entire representation. There's no gap that matters, between the learning algorithm and like reality. And when you would take that exact description and try to bring it to networks, you end up making all these like decisions where you're reducing that fidelity in some way. You're saying like, oh, I guess like this column is going to represent a single host on a network, and for every row element here, I'm going to set this to 0 or 1 to indicate like a service is open or not. And automatically you think about all the fidelity you're losing. You're like, wow, what version of the service? Like, do you have an understanding of port that's different from service? And it's very easy to get stuck in this like, is anything even happening here? Like, what are we doing? And the answer, like the thing that was different about Worlds for us was we had this opportunity to like LMs are just taking in text and putting out text, right? The layer we were interested in sort of simulating is this tool layer. So from the perspective of the language model, it decides to run some tool and then text comes back. And so our question was essentially like, can we send back text that makes sense to like format that in such a way that is like useful? And I guess that takes us a little bit to like what Worlds is, but it was this difference between like wrapping the simulation around what you knew how to solve versus like setting out to say like, I want to meet this level of fidelity that represents what an agent would see, and like that's sort of the North Star. So that takes us to Worlds, what Worlds is, the manifest sort of tool layer thing. And for that, I'm just letting Max talk. That's
yeah, so we have, there's a few different components here. The first one is a manifest. And a manifest is fairly easy to understand. It's just a read-only description of what exists in the network that you've generated. Um, it's pretty complex, and actually, I want to address something that you talked about, Shane. There's a doing this simulation is pretty difficult in a way because you think about and I've heard this a lot. It's like, oh, you simulated like all of Windows, Active Directory, like everything you'd want to do on a Windows network pen test. And it's like, people are just kind of blown away by that, or don't trust it. And it's
sure.
like, well, we have simulators for the entire world. Like we have video games that like simulate everything. It's
Yeah.
like, is this really so crazy? Um, there's really nice abstractions for the real world. A lot of the complexity is in physics, and physics is not easy to simulate. But we have some
You
good
do it all
formulas for it.
the time.
Windows is Windows environments are a little bit different because there aren't these like beautiful abstractions. It just takes, it's like Windows acts in a very particular way. And so like doing this process of, simulating what needs to be simulated in a Windows network is like very difficult. It's a very, very complex thing. And the way that comes to fruition is, we start with the manifest, and the manifest is just like what exists in this network that we're simulating. What are all the things that if you were to start a computer, start all the hosts in a network, like what would be sort of the base state, and then we have the tools, and the tools are what happens when you interact with that base state. What are the transitions that happen from you know doing before you ran the tool, and what happens after you ran the tool. Like what does this new world look like after you've executed that command. And those are really the two main things here. It's the what exists at the beginning, what exists after a state transition.
Yeah.
And very fundamentally, although again, like there's a lot more complexity behind it than that, those are kind of the two things to that world is built on.
Yeah.
And really,
Yeah.
really, I would imagine that any simulation is built on.
Yeah.
It's a pretty beautiful abstraction.
I'm super inclined to agree. And what's interesting is like a lot of synthetic data approaches that have emerged recently, like reading recent papers by the Mucha team with Kimmy. There's this sort of idea that you're able to simulate, like you just take all the trajectories you want directly from sort of like a language model of some kind. Um, and what that requires is that information is like embedded in the model. Um, Whereas we're sort of starting with this idea of like, oh, the models just don't know enough about Active Directory. They don't know enough about Windows to be as comfortable in it and as fluid in it as they are in software. So we're just like creating this sort of mathematical model, shoving those priors directly in, and then seeing what sort of takes place after that. So it's this sort of translation layer of like there's the math behind Windows that gets shoved into a simulation. We blow that representation back up to where we can actually use it, which is these like text trajectories that Worlds generates at the end, and then we use that as the way of like communicating that information directly to the model. That's it. That's what we did. And the I guess the ultimate test of whether a simulation is correct or not is how well you learn on it. So we would say Microsoft Flight Simulator is pretty good because you did not freak out when you were in a plane. Some of those priors transferred. You're still here with us. It sounds like it was pretty good. And we had sort of a similar idea of the test for the world's trajectories. So we generated around 10,000, relatively small for this test case. But what we wanted to figure out was, do these trajectories you're generating make a sort of meaningful difference? So we talked a little bit about the experiment we ran, which was based on Goad. So what came out of Worlds was this like full set of trajectories through various sort of simulated networks. And the question was, can we go from this to seeing better long form tool use reasoning over like a complex task, like going from 0 to domain admin on Goad? And what we found was that there were some steps needed to sort of augment those traces. There were two that were significantly from my side. One was the addition of synthetic reasoning. So this is not uncommon information to anybody, I don't think, but modern reasoning models sort of use opening and closing think tags to sort of describe, to reason, to describe their understanding of what their desired goal is and what their next action is going to be. And what we found is if you use those, just the tool call layer directly, a lot of that, like the model will learn, the loss will go down. That's not a problem, but you don't see as much change of inference time behavior. And it's not entirely clear whether that's something that's due to injecting more entropy into the traces or the trajectories with that synthetic reasoning, or just that models that are used to doing think tokens at inference time will sort of naturally do that while you're evaluating them. And because they're going to do that, once you've conditioned on those like think tags, anything you like pushed into the model that didn't have them is sort of going to be increasingly unlikely to come up when you're sampling. That's not clear. I guess we should talk about Nematron. I didn't talk about Nematron.
Not yet.
That would make this way clearer. Good thing we do that in the blog. So Nematron A billion is a Qwen 3 based model we thought was interesting largely because there were a lot of synthetic data techniques that were used on it. We linked to Tool Orchestra, which I believe is the paper associated with it. And essentially their like strategy that you're seeing sort of more and more commonly is to generate you're essentially looking for simulated ways to use tools. So what they do is they set up an environment, which is essentially like a SQL table, and then they have the ability to like query that for various things. And then for one of those sort of data models, they'll generate a bunch of like questions for the model to solve, and they'll get these trajectories that involve this like multi-form tool use and reasoning. So we thought that was a cool sort of, we just think synthetic data is cool. I think synthetic data is cool. So we wanted to use a model that sort of used that. So we evaluated that model, a billion parameter model, on Goad, sort of raw. Tori, you're the best. It's just like, just finding those links quick. The base results were essentially like, we show them in the blog. It got a 0 compromise score, which is just a sort of score we have. Like if you were to just score Goad based on how many domains you got, that'd be a fairly like low fidelity score. You'd get like a 0, 1, 2, or 3. Whereas we're interested in sort of being able to see the slow uprise of capability, make a good eval. The compromise score is just based on like what users were compromised, what hosts were compromised, etc. And Nematron got a 0, like nothing. Was not able to make any sort of progress. And what was clear from looking through the traces was that Nematron orchestrator did not know anything about like Active Directory pen testing. So I would say the most common, it looks like me in 2016, you know, like, all I knew how to do was run nmap, read Metasploit module, and lie. And that was
Eat hot chip.
Eat hot chip. And you know, it has that exact same energy as someone who just started getting into security and like, you know, did Metasploitable 2 and is like real jacked up about it. You know, you're just like the whole world is open to you as long as you do service enumeration and then you find a public CD that's associated with that same. Because
The
of course
filter's turned off.
Yeah, always turned off. And that was it. So it would scan. It would then run a series of like nmap scripts to see if there are any like open vulnerabilities associated with them. If it did or decided it looked like there was, it would load up Metasploit and just try to fire off Eternal Blue because there's an SMB server and like, you know, hold out for hope, baby. And when all else failed, it would load up a password list and just like start spraying. And that was a very consistent behavior. So we evaluated all of these over 5 different episodes, starting from scratch use time, and that behavior was like very consistent. And it would sort of give up after that. And I think that's a reasonable, like, if your model of pen testing does not include Windows internals, I think that's actually behavior that makes a lot of sense because you have you've pulled every lever you know how to grab, right, at that point. So the experiments after that were sort of just exposing the world's trajectory data into the model and seeing what sort of behavior changed. And the first step was taking just the raw tool call trajectories, running that through the model. Didn't see a massive change there. Like I said before, I think because without having some sort of reasoning traces, even if the data is being stored in the parameters, and I'm confident that it was because the loss went down, it wasn't in a way that was going to be available at inference time after the think tokens came out. Adding that synthetic reasoning actually ended up being sort of far less complex than Worlds as a simulator, but it was maybe the most interesting part to me because I found out how many ways there are to do that wrong. And I'll say that like the naive way of just like, you're looking for something reasonable and scalable and parallelizable. You're just like, I could generate think traces for each of these sort of tool calls. And if you do that in a way that's sort of sufficiently independent, and you look at the reasoning traces afterwards, you're like, yeah, that makes sense. It says something like, I need to know more about this host, so I'm going to run nmap. And you're like, yeah, that's so true. You're so smart. Yeah. And so I trained on that style of synthetic reasoning traces augmenting the world's trajectory, which is to be clear about the definition of the word augment. It is the same trace, just now it has two think tokens before the tool call. And what I got was this sort of memento model that could justify sort of anything without reference to what it had done in the past in a very reasonable way. So it would sort of have something along the lines of, I need to know more about host X, so I should like scan it over and over and over and over again. And it never actually like built on anything. So in some ways it actually performed, I would say, worse. Which was entirely because I poisoned its reasoning. Once that got fixed, and we added some failure recovery, that was sort of something that was added just because failures happen all the time in model trajectories, not in simulation. There's no reason to sort of model fat fingering things and getting error messages, but it does happen all the time on a test. And we've seen from like the DeepSeek R1 sort of like this new thing where you inject failures into trajectories just to show recovering from them. And that's just like part of covering your distribution. And, that's probably real. What percentage, Max, would you say of what percentage of commands during your career as a pen tester were correct?
0. the amount of times I was joking with someone on X about this. It was like accidentally running LS on a beacon when you open it up just because you want to run something and then you're accidentally in Windows System 32 and the beacon dies because it's trying to read every file, list every file in System 32 is like probably 90% of tests I've ever done. That's I've done that.
Yeah, that
sounds happens quite a bit.
Awful
yeah,
that made my stomach.
This beacon's going to be dead for the next maybe 5 minutes.
That's awesome.
Our sleep timer is 60. We can't even sleep this thing down. Yeah.
Well, and that's the other reason you would want to get trajectories from pen testing firms, right?
yeah, really.
So that we found, just because it happens to certainly happens to language models where they'll have particularly in our harness, we were using like bash as our tool. Essentially, we weren't really doing a lot of we'll call this tool scan, and we'll have all these arguments, and we'll put it exactly into the command the way you want it. And that was sort of for two reasons. One was because it was the most natural way to relate the tool layer in Worlds to a trajectory. Also, I think it was just a more interesting test to sort of see we're providing a bunch of tool examples. How much of those are really being burned into the model at what we would call full fidelity, right? Like what I would call a low fidelity scan was if we, instead of being able to interact with worlds with nmap, we were able to interact with this tool called scan, and we did piecemeal for every tool you can imagine. We tried to come up with some cleaned up compressed API. It's just more interesting to interact at the precise layer of your tools, which is what we really you. I just used your data. But what the royal we did. So sort of adding those failure trajectories and the synthetic reasoning, we were able to get to our result, which is going to come up. Maybe. Am I sharing?
Not yet. You just made
Not yet.
yourself big.
There
Oh,
It's thinking about it.
dude, you're huge.
I'm quite large. There you go.
We're
So
good. We're
that's Restream working it out. So we were able to get this sort of final result here, and it was a step change, right? And that's clear from like looking at the bar chart. The evaluation was even for all three of these models, but the performance was extremely different. And looking at the difference between even like the base model, but also like the model that was just tool calls versus like the synthetic reasoning that I think made it able to actually implant the knowledge from the tool calls into the model. Suddenly, this model that had been only running Nmap and Metasploit is like, oh yeah, I gotta AS repros this guy. I gotta crack this. I gotta dump LSAT. Like it was just a very different level of sort of performance and a different way of approaching the problem, which I was really impressed by. And to me, that was like the thing that showed that we were 100% on the right track with Worlds, is that we could like just SFT, not even like any offline GRPO on the trajectories or anything, just straight up supervised fine tuning on a LoRa on an 8 billion parameter model, see this sort of difference in what I would consider like a pretty long form, we're talking 20 to 30 tool calls to go from 0 to north domain, like in a row. Really, really cool results. And now I'm big again. I don't want to be big.
Yeah, I mean, like that's such a crazy change. It's literally infinite growth. You go from
Yeah, that's
0
right.
to 30.
That infinite growth. I am not doing that. It's just making it bigger.
But yeah, so like I guess to recap, so to start, we have our harness and our environment run the 8 billion Nemotron on that environment, and it got 0 for our custom score. We take the world's data, so manifest and tool calls, we generate trajectories of essentially fake pen tests. Tried that out, didn't really improve the model. Then we added that synthetic reasoning, and added the synthetic reasoning and didn't really work. But that did a way more intelligent, and actually your solution to that was like incredible. Did a really intelligent way of generating those thinking traces. Added failure recovery, and tried it again, and we got incredible infinite growth results.
Infinite growth. Yeah. So if you were to chart this out, I mean, by next month, it should be the smartest model that ever lived. I mean,
True.
we're just straight watch the line go up. Yeah, it was it was a great proof point for your simulation. Essentially, I felt like my role in this project was mostly like the vibe check of the simulation. like yeah, we'll see. Like the fidelity looks good. Let's try it out. It was kind of the thing. And what was really is most exciting about it to me is like how replicable the broad strategy is. I think this is certainly like the particular use cases in Go do not represent like all of the stuff that's interesting or relevant about security, but sort of expanding horizontally to cover these additional use cases and these additional scenarios, I think is going to be super interesting. Particularly once we can get like when defense is included to a similar level of fidelity, we can start to go back to your prior research on the red versus blue at this sort of like larger synthetic scale. It's really pouring gasoline on what was already like a very reasonable setup to see sort of improvement.
Yeah, but the difference, the kind of what I was getting at with the first couple blog posts about AMZ, I mean, that was just PowerShell. The defender in that case was an AMZ provider. The attacker was a PowerShell / Lua agent. It's like this is a network pen test. Like and the defensive part is, like there and getting better. So that's just a way more interesting and large problem that, this technique allows us to implement.
Yeah.
And, the other thing that's kind of exciting to me is, as we like, we're not relying on like, the only thing we're relying on is the simulation to get better and the sampling mechanism to get better for those trajectories. It's like, as those things improve, more, tools, techniques are added, that provides more data, like diversity of data,
Yeah.
which, you can use for, I don't even know what you do. Train models. I don't even know how that works. You buy GPUs, but like, I
Tokenize
think that's
things.
the most. Yeah, what is a token, dude? Uh, but it's like, I think that's such a cool, like, incredibly, like, just incredible, like, mechanism of like, as the world, like, model improves, the the end model improves, as much. And there's going to be a lot of, uh, you know, you have way more tricks up your sleeve. You talked about GRPO, instead of just SFT. There's a lot more we can do and explore here. Um,
100%.
but getting that data, a super diverse data set, just with more engineering work is like really, really awesome.
Yeah, and there's a lot of like we've been in a situation, like the royal we that I use to encompass all of security, right? Where data is expensive, so you don't get to be choosy about that data. And there's been a growing amount of research that's been super interesting. A lot of the guys like working at Datology, for example, that are like, well, if you're in this like data rich environment, or you have this ability in particular to generate your own data, you have access to more interesting, sort of more efficient scaling mechanisms for like pruning that data such that you're only training the good stuff, and you're getting essentially smaller, better, faster. And that has really like, there are a lot of papers that I read, 6 months ago, and I was like, oh, I wish that was me. And now I'm like, that is me. I'm pulling those back off the stack. You'll see them sort of grow in the background here over the next sort of weeks and months. Um, that I'm really excited to get into, for sure. And I guess we're ready for questions, or we can just keep talking to each other. I'm not seeing a lot of questions in the chat. The sim engine is some peak engineering IMO from Joe Burton. True. Max is a
Real.
peak engineer. I mean, it really is like, I don't know who wants to hear this except Max, and probably not even Max, but it really is a pleasure to work with someone who is like so competent. Like I am frequently in the position both of like, as the data guy, to be like, I just need this data to be better, like, and translating that into something that is like meaningful and turning it around and getting like this kind of result. It's just like, it's really awesome. So it is peak engineering. Mr. Burton is correct.
Dude, I don't even know what I'm doing. You're the guy training freaking models.
The bars
No.
only go up because of you, man. There are no tricks I could do if the data was bad. I mean, if no one asks a question, we're just going to talk about your flight sim again. I think that's sort of the most interesting.
Yeah, dude, we could talk about flying.
We can talk about flying.
Yeah.
Yeah.
We can just go on a riff.
Yeah, we can just
What's happening?
ramble indefinitely. All right, folks, this has been a pleasure. If you've got any questions, feel free to drop them in the comments. This stream will be posted after this. Max and I will be reading the comments. Tori will make sure we read the comments, and we'll reply. Otherwise, expect more research to come out in the next weeks and months as we continue to work on the world's thing. Appreciate your listening. Oh wait, never mind. Evan in the chat, thanks for sharing. We did not, in this case. The only comparison we did for models, sorry, Tori, can you put that up in the chat? Yeah, thanks, Tori. So the model comparison was just Nemotron before and after sort of exposure to the world's data. And that was sort of our test of fidelity. It's totally reasonable to have another like dimension of that being like which model sort of responds best to this. And I think it's totally reasonable that a Microsoft-based LLM might have a different sort of baseline understanding of sort of Windows technologies. Didn't try that. It'll be interesting, though. I'll say we're probably most interested in scaling up the size of the models next, like 32 billion and 70 billion parameter models, and seeing, do we see similar improvements across those larger sizes? And, ultimately, can we just forget one, go domain? Let's do three. But great question.
Yeah, and I think kind of the point here is like what we're testing is, how does a model improve, like a single model? We're not really testing like, every model because that's sort of a different evaluation. The evaluation we're more interested here is like, if you have a model and then do SFT on it, like does it improve? And mixing models maybe isn't exactly what we're trying to do with this
Yeah, I
experiment.
think if the experiment had been like, we just want the single model that is best, then probably would have started by evaling like all open models of a similar size and then applying this data recipe, whatever that was. But it was really, like Max said, it was just about seeing like, does this data recipe improve a model? Like, can you start with something that is essentially like not competent in a task, and through that purely synthetic data, get there? Joseph Burton.
But that is a good question. It'd be interesting to try next.
It would 100%. Joseph Burton says, might have missed it. Did you mention if you code the tooling into the data or just let the model have at it with the MCP tooling? So the way that for this particular experiment, what the trajectory worlds generated were trajectories that looked like if you were just typing into bash, essentially. And that was sort of done basically as a challenge. Like, it's more interesting. You can imagine that we might have like very specialized MCP tooling. So instead of having like raw access to Nmap, it was like scan, and it took like a host and it supplied all the other flags, and then the data came back cleanly. It was sort of more interesting, both as a challenge of Max's engineering capabilities to keep that fidelity like 1-to-1, but also from the model's perspective. That was sort of what is very different about Worlds, I think, from other like simulation projects I've seen in the past for security, is we're starting by like as far from abstraction as possible. Like,
yeah.
I talked a lot on that one. Do you have anything you wanted to add about, besides the fact that it was hard and I made you suffer?
No. I mean that's pretty much it. Like it's like we're doing it. Not doing MCP. Like we probably honestly would have had potentially better results if like there was some sort of calling structure like that. But
Sure,
we made it hard on ourselves and it like but in a good way. Like I think that
it's
really proves the idea.
Yeah, it's a more interesting test of the capabilities for sure, where you want to like it's very easy. So like the classic RL simulations that I talked about earlier, they're all very like high level, like your actions are like, I can scan a host or I can exploit a host, and like, what do you mean exploit a host? Like, what is, it's very easy to get to a place where a simulation is so abstracted that it could be about anything. Like I've seen people sit me down with like, this is security and this is a scan and this is whatever. And like, this could just as easily, you could tell me like, this is a soccer game and these are players you can pass to and you can like look or you can kick, like, and if that simulation is too abstract, essentially, then the priors that you're essentially just saying like, can I learn the priors from that simulation in a way that never lets you go out into the real world and then do anything with that. So the commitment to the direct sort of like batch representation prevented us from hiding, I guess, any of that stuff. Great question, Joseph. Thank you. That's the chat. All right, we're over an hour. So we will take more questions absolutely in the comments, and appreciate everyone's time. Like I said, there'll be plenty more worlds research coming. Stay tuned. Tori, play us out. Oh, that feels so good.